So now that we've seen how to get this bell-shaped curve out of creating samples of means, let's talk about the actual center and spread of this curve. So when we work with sampling distributions of means, we'll always have to check that central limit theorem first. So with that, we'll want to make sure we have independence, random sample, and then we'll check that sample size condition. And then again, with that sample size condition, if we know it's already normally distributed, we don't really need to have a large sample size. But if we don't know the distribution or if it's skewed, then we'll check for that sample size larger than or equal to 30. So we'll look at both cases in terms of wording of what if it's normally distributed and what if it's not normally distributed. So what we want to end up with is this curve. And this curve should be describing the means from our sample. So what's going to fill up this curve is all these different possible means from some certain sample size that we're using. And we want to know how do those averages distribute. So what we noticed in the previous video is that the center of the distribution stays exactly the same. So that's what this notation is showing right here. So that notation with the mu with a subscript of x bar, that's just describing the average of the sample means. So in terms of the center of our curve, it's just going to be the population mean, so we just copy that over. What we need to calculate is the standard deviation of sample means. And with the standard deviation, what we'll end up doing is taking our population standard deviation, so that's what's making up our numerator, and then we'll divide by the square root of our sample size. And that's where our sample size takes effect. As we saw in the previous video, how taking larger sample sizes create a more restricted curve. It is a lot thinner. And then if we decrease our sample size, it kind of starts to spread out. And it's because of that denominator right there. The idea being, if we're taking a large sample size, then we would have a very big number in that denominator. And if we divide by something large, it creates an overall small value. Whereas if we have a small sample size, like a sample size of 2, we're not really dividing that much. That population standard deviation isn't going to decrease that much. So that's where we can see sample size take effect. So what we're going to have then is, whenever we work with these sampling distributions of means, in terms of a distribution, if we pass that central limit theorem, we'll know it's normally distributed. For the center of the curve, we just use our population standard deviation. And then for standard deviation, we take population standard deviation divided by square root of sample size. And this is going to be a distribution of means. So where I have x there, you could actually imagine that this is a distribution for x bars, so little sample means and how they'll move around. So with that, let's look at an example. In this video, we'll go through an example where the population is normally distributed, and then we'll look at an example in the next video that has a population that's skewed. So here we go. They're measuring glucose levels 1 hour after ingesting a sugary drink. And what they tell us is that this data has a normal distribution to it. So with that, we know our population has a nice bell-shaped curve to it. And then they tell us the mean, and they tell us the standard deviation. So with that, this curve that they're describing here, that's bell-shaped, centered at 125 with some standard deviation of 10. This description is for individual glucose levels. So it's not from taking samples, it's not from taking averages, it's just for individual people and how their glucose levels will behave. So that's where I put in this first question here. They ask about a single glucose measurement and what's the probability that it's greater than 140 milligrams per deciliter. Now, if it's just looking at exactly one value, then we just go to our old methods. We don't need to think about our sampling distribution of means yet because we aren't collecting a sample. We're just looking at a single value. So with this question, we'll use our distribution centered at 125 with a standard deviation of 10. And with that, what we're going to do is find this probability of what's the probability of being at 140 or greater. So with that, we go through our old methods. We'll get our z-score first. So we'll take 140 minus 125 divided by 10, which is a z-score of positive 1.5. And then we'll use our table to help us find the probability that z is more than or equal to 1.5. So since we're doing an area to the right, we'll need to take 1 minus, and then we go to our table and look up positive 1.5, which is landing at a 0.9332. So with that, we take the complement of that 0.9332, which will give a 0.0668. So with that, we have a probability for a single glucose measurement. There would be this 6.68% chance a single glucose measurement is greater than 140. All right, so that's just kind of review of what we did before with the normal curve. Now when we get to this next question, if measurements are made on 3 different occasions, so now what they're doing is they're bringing in a sample size. In that previous question, it's kind of like our sample size is 1, but we're just looking at a value. It's not really a sample size. We're just looking at individual pieces. But here we're collecting a sample. So we have these different outcomes. And then what we want to do is look at the mean of them. So this whole idea of relating a sample size and the average and eventually talking about probabilities with that, that's going to be the setup for these sampling distribution of mean questions. So we'll look for those pieces of a sample size and asking about the average. Now this question asks us to talk about the conditions and if we pass the conditions. So this is really checking our central limit theorem, which that first piece asks about if we have independence. So that means when we take the samples that the outcome shouldn't be influencing each other, which we have here. If you take the glucose measurement of one person, that isn't going to affect the glucose level of another person. So we have independence. You could also think about that 10% condition here, the fact that we're only talking to 3 people out of everyone. We're sampling less than 10% of the population, so we'd have independence. So you could think about that 10% condition as well. Randomization. Now what we want to look for with randomization is that somewhere in the wording it should say that it's a random sample, and they don't say that here. What we're going to go ahead and do is just assume they're good researchers. So sometimes we'll just assume that that's fine. When they collect it, it should be random enough. And then for sample size, so if we go with our rule that we should have at least 30 people in our sample, we fail in that with a sample size of 3, this is very small. However, our population is normally distributed. So up here, we're starting with this bell-shaped curve, so it doesn't really matter the sample size we use. When we collect our samples, it'll still be normally distributed, so it'll kind of mimic what's happening in the population. So with that, even though our sample size is small, we have the population is normally distributed. So with that, we pass all of our conditions for the central limit theorem, which basically tells us that if we do collect these samples of 3 people and look at the means, then our curve is going to be bell-shaped. And that means we can do all sorts of probabilities and things. Define the sampling distribution and its parameters. So our parameters is going to be that population average and that population standard deviation for our sample means. Now the population average for these sampling distributions of means, you just copy that population average from your original population. So that's just going to be 125. So no calculation there. But the standard deviation we need to adjust for our sample size. So we take our old standard deviation, which was 10, and then divide it by the square root of our sample size, which is 3. So that's going to be a 5.7735. So for a distribution of our sample means, they'll be normally distributed, centered at 125, with a standard deviation of 5.7735. So now we have this curve set up that we can start calculating probabilities. So this next question goes into asking about probability of seeing certain means. So when you have these questions that relate probability and they mention mean or average, and then we have a sample size, those are the key pieces to show it'll be a sampling distribution of means. So we want to know what's the probability that the mean is greater than or equal to 140 milligrams per deciliter. So because it's a question about the mean, we want to use this distribution that we just found. So centered at 125 with this standard deviation. And so with that, our picture is going to look kind of the same. If we set up a good number line here using standard deviations, 140 is going to be further out than it was before. So with this, we're finding a very similar probability, but now we have a different spread to the data because of the averages. But our steps will be the same now, so we'll get a z-score for 140. So we'll have 140 minus 125, but now we want to use that standard deviation of 5.7735. So that's going to give a z-score of 2.598, which we need to round to 2 decimal places to use our table. So we'll use a 2.60. So we want to find this probability of our z-score being larger than or equal to 2.60. So with that, when we go to the table, we'll use a complement 1 minus. And if we go to our table and look up 2.60, that'll show us a 0.9953. Which, when we calculate that, that'll be a 0.0047. So now, in terms of phrasing for the solution here, where before it was a 6.68% chance a single glucose level is greater than 140, now what we have is that there's a 0.47% chance the average of 3 measurements, let's say 3 glucose levels, is greater than 140. So our wording changes a bit because now it's about the probability of an average occurring with a certain sample size attached to it. We can also ask questions about percentiles. So what's the 95th percentile for the average of 3 results? So we can ask about cutoff scores, but again, it's asking about how is a mean behaving with a certain sample size. So with that, we want to use the same distribution for our means. And what we want to see is where is the cutoff such that 95% of the data is to the left-hand side. So with that, we go to our table and we look up for the spot that has 95% of the data to the left. And with that scenario, we should be getting a z-score of 1.645. And then what we can do is we want to convert this into a glucose level. So we just need to convert where we have a z-score of 1.645. And that's coming from some x value minus the mean over our standard deviation. And then we just need to solve for x. And we should get an x value of 134.4974. So with that, the cutoff for the 95th percentile is about 134.5 milligrams per deciliter. So with this, it just takes reading carefully in terms of what type of probability are they asking for. Is it just an individual value? Because then that's like part A, and we just use the methods we learned previously. But if they start relating it to a sample and a mean, then we need to form the sampling distribution of means.